How can the universe allow time loops on paper, yet collapse into paradox the moment we try to imagine them as real? The equations seem willing, almost inviting you to entertain the idea of stepping into yesterday, yet every attempt to picture such a journey dissolves into contradictions. Some physicists say the loopholes can work, others insist they implode. And somewhere between those arguments lies a mystery that feels older than science itself. Welcome back, traveler. Tonight we drift through science. You're lying wherever you are, maybe in a dim room, headphones soft against your ears, the world quiet enough for curiosity to breathe. The kind of quiet where even complicated ideas turn gentle. And if this slow exploration brings you comfort, if it helps you untangle the weight of a long day, leaving a like and subscribing keeps this little corner of calm alive for nights like this. If your mind is restless, if sleep feels far away, or if tomorrow seems too heavy to greet, you're not out of place here. Ideas about time travel are confusing even to the people who study them for a living. You don't need to catch every detail. You don't need to solve anything. Let the questions move around you the way distant stars do. Glimmering, drifting, not demanding anything from you at all. Tonight we'll wander through the strange terrains that physicists argue about, the places where space-time folds, where wormholes flicker at the edge of theory, where particles dance in loops that seem to rewrite their own histories. And along that path, we'll pause inside laboratories where lasers hum, equations stretch into impossibilities, and researchers adjust mirrors or code, trying to coax clarity out of competing truths. Time travel is a puzzle studied not just in blackboards and simulations, but in the hands of real people searching for coherence. So settle in. Loosen your shoulders, let the dark soften around you, and let whatever thoughts you carried here drift to the edges for a while. Tonight we'll walk slowly into the question so many brilliant minds dispute, not to answer it perfectly, but to see how the universe behaves when you push on the edges of time. And somewhere in that quiet, a doorway begins to open. You feel as though you're floating just above a quiet, pale landscape, an empty stretch of space-time drawn out beneath you like a sheet of frost. Nothing moves around you, yet the silence carries a peculiar tension, as if the fabric below is waiting to ripple. You can almost sense the strange rules that govern this place, rules that seem to shift depending on how closely you look. This is where the earliest hints of time distortion first appear, subtle enough to overlook, yet profound enough to unsettle the entire idea of a linear past. The physics that shapes this stillness begins with Einstein's realization that time isn't a universal rhythm ticking independently across the cosmos. Instead, it stretches and relaxes depending on speed and gravity. If you move fast enough or fall deep enough into a gravitational field, your personal flow of seconds drifts away from everyone else's. It's a small step, but it cracks open the door to the possibility that time is bendable, maybe even loopable, if the conditions are extreme enough. One concrete example sits close to home. GPS satellites orbiting Earth run on clocks that drift by microseconds per day because they move fast and feel weaker gravity. That tiny mismatch would break navigation entirely if engineers didn't correct it. The difference is small, almost invisible to you down here, yet it proves something staggering. Time is elastic. And if something elastic can be stretched, physicists start wondering if it might also fold. In labs, researchers test these distortions with laser-cooled atoms suspended in vacuum chambers. They watch atomic clocks, devices so precise they gain or lose a second only every 15 billion years, tick differently depending on elevation. A clock on the top shelf ages faster than one on the bottom. Students double-check cables, adjust calibration lasers, and stare at screens where tiny variations appear like whispers, revealing the limits of intuition. Time refuses to behave as a single shared drumbeat. and every experiment seems to deepen the divide between theory and lived experience. If you imagine time as a long ribbon, you can almost see it sagging slightly where gravity presses, lifting slightly where velocity stretches it thin. Nothing breaks, nothing tears, it simply reshapes. And as you picture that ribbon shifting under invisible hands, you sense why scientists argue, if a ribbon bends, what stops it from bending so far that it touches itself? Thinking about this doesn't need to make you anxious. You're still lying wherever you are, breathing steadily, held by gravity that's gentle compared to the cosmic forces out there. The universe can be strange while you remain safe inside your quiet room. And even if the questions feel too big, you're only listening, not solving. Imagine again the landscape beneath you, but now you notice a slow tilt in its structure, as though the floor of space-time dips in the distance. That dip, if magnified enough, becomes the curve that general relativity predicts. It's not a fantasy, it's observable. Each distortion hints that time doesn't unfold in a straight line, but in a geometry that responds to mass and motion. It's a soft but essential step toward understanding why the idea of traveling through time sparks debates that never fully resolve. To ground this idea, consider that light traveling past the sun arrives slightly later than expected because space-time curves around the star. That delay, measured during a 1919 eclipse, was one of the first confirmations of general relativity. Telescopes captured starlight bending, and with that bend came the realization that space-time behaves like a pliant surface, one that could, under extreme circumstances, fold deeply enough to confuse past and future. Astronomers today recreate that experiment with far more precision. They track quasars, bright beacons billions of light-years away, and watch their apparent positions shift as their light passes near massive galaxies. Teams in signal processing labs sift through noisy data, adjusting algorithms, comparing models, debating uncertainties. The bending is tiny on the sky, but it's real and relentless, showing again that gravity sculpts the stage on which all moments play out. It helps to think of space-time not as a clock tower with gears, but as a pond. Drop something heavy, a star, a black hole, and ripples form. Your life unfolds on the surface of that water, gently riding the waves. And because every object makes its own pattern, no two observers experience time exactly the same way. That's not a glitch, that's the architecture of the universe. And if waves exist, so do rare places where they concentrate and threaten to fold inward. When physicists argue about time travel, they're really arguing about whether these folds can deepen into loops. Some believe the math allows it, but the universe forbids it. Others believe nature might tolerate the occasional loophole, quiet, fleeting, hidden from collapse. You don't have to choose a side. Decisions about impossible curves can rest without resolution. While you lie here in the dimness, you can simply observe how strange it is that time isn't rigid, that your seconds are not the same as those on a satellite, that the universe already behaves like something far more flexible than intuition suggests. Think again of the ribbon, gently warped, slightly uneven, never perfectly straight. That unevenness is the seed from which every argument about time travel grows. If the ribbon were perfectly flat, the conversation would end. But it isn't. And because it isn't, every physicist is forced to confront a possibility that refuses to stay quiet. You're not expected to judge them. Their disagreements are part of the process, just as your wandering thoughts are part of resting. The confusion isn't a failure. It's a sign that the universe still has layers untouched by certainty. And as the landscape beneath you shifts again, just a subtle deepening of the curve, you sense that the next mystery grows from this one. Something farther ahead in the fabric bends more dramatically, almost as if the space-time you're drifting over is inviting you to follow that descent and see where the arguments truly begin. You drift through a dim corridor of space-time where everything feels stretched, like a hallway made of softened glass. The floor beneath you seems to slide backward at a slow, syrupy pace, giving you the sense that even standing still would change how time moves. This is the realm where motion begins to peel apart your expectations, where speed becomes a sculptor, tugging at the minutes and hours as if they're made of fabric rather than something rigid. As your awareness settles into this moving corridor, a subtle insight surfaces. Motion isn't just about changing location. At high speeds, motion alters the very rate at which you exist, slowing your personal clock compared to someone who stays behind. This isn't fiction or philosophical speculation. It's a measured, repeatable phenomenon, one that quietly reshapes every conversation about whether time travel is technically allowed. Muon particles born in Earth's atmosphere provide one of the clearest demonstrations. They decay in microseconds, far too quickly to reach the ground, unless they're moving near light speed, and yet detectors at sea level routinely capture them. Their internal clocks tick slower because of their velocity. By all classical expectations, they shouldn't survive the trip, but relativity gives them a longer life. It's a small loophole, but a loophole nonetheless. In laboratories, physicists recreate this effect using particle accelerators. They inject protons into magnetic rings, spinning them around thousands of times per second. Screens glow in dark control rooms as researchers compare predicted decay rates with the strangely cooperative behavior of particles that refuse to age normally. Some stare at the data with awe, others with skepticism. The disagreements begin here, because if speed can stretch time, then how far does that stretching extend? Now imagine standing at the edge of a long train platform. You're still, the rails are still, yet a train flashes by at relativistic speed. From your perspective, its onboard clocks run slow, but from the train's perspective, you're the one aging faster. Both views are correct. This mutual bending of time creates a puzzle with no single privileged perspective, and that alone is enough to ignite decades of debate among physicists trying to define what happening even means. The metaphor that rises is simple: two rivers flowing at different speeds. Neither river is wrong about its own pace. They simply move through landscapes shaped differently by gravity and motion. And once you accept that streams can diverge, you begin to sense why creating a loop or bending one river back onto itself doesn't immediately shatter logic. Yet you remain here, breathing softly, untouched by the frantic velocity of particles or the restless disagreement among physicists. Your pulse stays slow, your room steady, while somewhere in the universe particles outrun their own decay, hinting at paths that might circle time itself. You don't need to solve anything, just observe how strange possibilities accumulate like frost on a window. In astrophysics, neutron stars offer another clue. These collapsed remnants spin hundreds of times per second, curving space-time with such intensity that time near their surface can run significantly slower than time far away. Telescopes capture their pulses, regular flashes that reach Earth like the ticking of impossible cosmic clocks. Each pulse reveals something peculiar. The stronger the gravity, the slower time crawls. And so the question deepens: what happens if we push this to extremes? Teams using NASA's NICER instrument on the International Space Station study these pulses in detail. They adjust models, cross-check timing data, and argue over competing interpretations. The numbers fit relativity well, yet small anomalies always slip through. In those anomalies, the seeds of disagreement grow. If time itself stretches in the presence of speed and gravity, where is the boundary that prevents it from looping? Think of time here as a braided rope. When motion increases, the rope thins. When gravity intensifies, the rope thickens, but in both cases, the rope is flexible. And flexibility implies the potential for knots, structures that might twist part of the rope backward, allowing events to overlap in ways we struggle to visualize without breaking logic entirely. As this thought settles, you feel yourself almost hovering above the rope, watching its fibers shift. Each fiber is a possible world line, one way for a life or a particle to unfold. Most fibers run straight. A few bend dramatically. And a tiny handful flirt with the possibility of turning back. The disagreements among physicists begin to make sense here. They're peering at the same rope, but focusing on different fibers. You don't need to untangle anything. Just breathe and let the image drift. Some knots may be mathematical illusions. Others might be physically achievable. The room you're in remains calm, steady, unknotted, while the cosmos experiments with patterns far beyond your everyday experience. Meanwhile, high-energy cosmic rays strike Earth's atmosphere with velocities nearly indistinguishable from light. Their behavior echoes the moon's, but on grander scales, reinforcing the idea that extreme speed warps time in ways we can't ignore. Satellite-based detectors log the events, while physicists debate what these particles imply for time's boundaries. Each team interprets the data differently, adding fuel to an already complicated disagreement. You can picture these particles as sparks flying off a grinding wheel. Bright, brief, unpredictable. But unlike sparks, they carry messages about how time flexes when pushed to its limits. Those messages never arrive in perfect clarity, which is why arguments persist. Nature whispers the rules, never shouts them. And as you imagine these sparks quieting into darkness, a final thought drifts through. Whenever speed reshapes time, it also reshapes causality, the sequence of cause and effect that structures your life. If causality trembles, physicists see an opening to challenge what traveling through time might mean. And openings like that rarely close without controversy. Yet while the debate continues, your world remains soft and unmoving. You're not being asked to race near light speed or to reconcile competing theories. You're just listening, letting your thoughts settle like dust in a beam of fading starlight. And somehow, the corridor you drift through begins to widen, not in a sudden shift, but in a slow unfolding that hints at deeper distortions ahead, as if the landscape of time is preparing to reveal a stranger shape than speed alone can explain. You find yourself drifting above a silent plain made not of soil or rock, but of softened space-time, stretching gently beneath your feet. The air, or whatever passes for air in this imagined landscape, feels thick and slow, like honey caught in a reluctant breeze. This is where gravity becomes an artist, reshaping time with curves instead of cuts. You stand still, yet you sense the seconds pulling apart, elongated by the invisible weight beneath the surface. As you settle deeper into this scene, the first idea unfurls. Gravity doesn't simply tug on objects, it tugs on time itself. The stronger the gravity, the slower time moves. This isn't poetic exaggeration, but a measurable truth, confirmed over decades of observation. Even your phone's GPS relies on this principle. Satellites experience slightly faster time because they orbit farther from Earth's mass. And without correcting for that difference, navigation would drift disastrously off course. At Harvard in 1959, two physicists, Pound and Rebke, performed an experiment in a tower that would eventually make its way into every modern textbook. They measured how gamma rays traveling downward were subtly blue-shifted by gravity. It wasn't the energy that fascinated physicists as much as what the shift implied. Time below moved more slowly than time above, a difference so small it could barely be detected, yet so real it reshaped the physics of the century. Allow yourself to imagine standing inside that tower. Metal staircases hum under fluorescent lights, and the measuring equipment sits like quiet guardians of a mystery humans weren't meant to notice. Technicians hold their breath as they adjust sensors with trembling fingers, unaware that their work will define the modern understanding of time. They didn't find an answer to time travel, but they did open a door. The metaphor here is a soft depression in the fabric of a blanket. Place a heavy stone on the blanket, and anything nearby tilts toward the dent. Now imagine that instead of fabric, the blanket is time itself. The stone doesn't just pull objects inward, it slows the very unfolding of moments. And if gravity can create depressions, physicists argue endlessly about whether those depressions can fold deep enough to loop back on themselves. For now, you breathe slowly, lying in your quiet room while continents of space-time curve beneath cosmic masses far away. You don't need to understand tensor fields or geodesics, you just need to sense the gentle truth. Time is not uniform. It flows differently depending on where you are and what surrounds you. Near a black hole, this effect becomes extreme. As mass collapses inward, gravity intensifies to unimaginable levels, stretching time until it nearly stands still at the event horizon. Astronomers observing stars orbiting the giant black hole at our galaxy's center, Sagittarius A, have measured this slowdown directly. Light from those stars arrives slightly redshifted, not only because of motion, but because time itself drags more slowly in that environment. In a dim control room at the European Southern Observatory, teams compare spectra gathered over years. They adjust calibration curves, recheck atmospheric corrections, and argue quietly about the best interpretation. Some believe these distortions could one day allow glimpses into the nature of time loops. Others insist the gravity near black holes seals time, preventing backward flow. Agreement remains distant. Picture yourself hovering near this cosmic abyss, watching photons strain to escape. They move at the speed of light, yet appear exhausted, their journeys elongated by time's distortion. The scene resembles dust falling slowly through a bright beam, except the dust never quite reaches the ground. This infinite delay has inspired dozens of competing theories about whether such regions hide shortcuts through time or merely illusions of possibility. Philosophically, the thought settles into something quiet. If time can slow to nearly nothing, perhaps its flow isn't absolute. And if the flow isn't absolute, maybe the agreement among physicists collapses because they're trying to define something that refuses to be pinned down in a single way. Time seems to behave differently depending on how hard you push it. Meanwhile, in laboratories around the world, atomic clocks tick with relentless precision. The ones elevated by only a few centimeters above others run slightly faster. Tiny differences measured in nanoseconds accumulate into undeniable proof that gravity shapes time. Scientists recalibrate devices again and again, arguing not about the measurements, but about what the measurements mean for the possibility of traveling through time. Imagine walking between these clocks, each ticking at its own pace. The room looks ordinary, white walls, polished floors, quiet hums. But each clock represents a slightly different universe. A foot higher, and your future arrives a little sooner. A foot lower, and you age a little slower. Not enough to matter to your daily life, but enough to matter deeply to physicists trying to map the possibilities. The metaphor takes shape like a multi-story house with floors suspended at different moments. Move upward, and the hours stretch more easily. Move downward and they compress. The structure never collapses, but its flexibility challenges the idea of time as a straight corridor. Corridors with uneven floors tend to bend. It's in the unevenness that disagreements thrive. Some theorists see these distortions as invitations, hints that tunnels through space-time might exist where time loops become allowable. Others argue the distortions are merely slopes with no way to turn back. You breathe slowly as these debates echo through academic halls, carried by chalk dust and the scratch of equations on blackboards. Deep underground, in gravitational wave observatories, detectors listen for ripples caused by massive collisions. When two black holes merge, space-time shudders, stretching and compressing time in passing waves. Physicists at LIGO and Virgo stare at screens when these signals arrive. Sharp peaks rise from noise like whispers of events occurring billions of years ago. Some wonder whether these ripples hint at more than vibrations, perhaps at regions where time's surface folds rather than ripples. Let yourself imagine these waves passing through your room, gentle as a breeze, shifting time by an amount far too small to feel. But mathematically, such shifts prove that time has texture, stretchable, moldable, maybe even tearable. And where there is texture, there is the possibility of hidden seams. The disagreements among physicists intensify here, where texture becomes theory. Can time tear? Can it fold? Can it reconnect? Evidence is sparse, interpretation abundant. Conferences fill with voices proposing contradictory models. Some argue for wormholes, others dismiss them entirely. Yet all rely on gravity's ability to distort time, the same foundation that began in that Harvard tower. You remain still, letting the noise of debate fade into a soft hum. What matters for you is the sense that time is not a single river but a watershed with many tributaries. Gravity shifts their courses, and speed stirs their currents. Travel becomes a question of navigation, not brute force. In this quiet moment, a final image arises, a vast terrain of valleys and ridges made of time. Some valleys sink so deeply that light itself struggles to climb out. Some ridges rise high where time runs freely. And somewhere in that landscape, hidden by the fog of equations, might be a path that turns back, not abruptly, not violently, but like a trail curling behind a hill. Whether that trail truly exists is what physicists can't agree on, but the uncertainty itself is a kind of invitation, hinting that the next layer of this mystery lies not just in gravity's pull, but in something even subtler that gravity whispers to. And as that whisper fades, another shape begins to emerge at the edge of thought, suggesting that the disagreements deepen, not because gravity distorts time, but because something else distorts causality itself. You picture yourself hovering in a quiet, dimly lit hallway that stretches endlessly in both directions. The floor beneath your feet feels warm, as if moments have been passing over it for ages, leaving behind a faint glow. Each door you see is labeled with a time, a year, an hour, a heartbeat. You feel that if you opened one, you'd step directly into another moment of your life. But something stops you. The uneasy sense that opening a door might also close another forever. From the scientific view, this hallway represents the structure physicists call causality, the principle that cause must precede effect. You drop a glass, then it shatters. You speak a word, then the sound reaches another person. This order is so ingrained that breaking it feels unnatural, even frightening. Yet time travel theories poke relentlessly at these boundaries, raising the question every physicist hates to answer: what if effects can influence causes? One of the earliest attempts to test this idea came from particle accelerators in the mid-20th century. Physicists at CERN studied kaons, unstable particles with strange asymmetric decay patterns. Their behavior suggested that time might not always flow the same way for every fundamental process. It didn't prove time travel, but it opened a crack, a suggestion that nature may tolerate violations of symmetry we assumed were absolute. Imagine standing beside one of those early accelerators. The machine hums like a metallic heartbeat, cables snaking across the floor like veins carrying electricity. Scientists in lab coats adjust knobs and scribble frantic notes while green oscillating screens spit out data. No one there is thinking about science fiction, They're simply trying to understand why particles refuse to behave politely. You feel the metaphor forming. Causality is like the stitching on a quilt. Each event is sewn to another in sequence, thread by thread. If the stitching loosens, the fabric still holds for a while, but pull on the wrong thread and an entire corner might unravel. That possibility is what keeps physicists awake at night. Philosophically, you lie in your bed and feel the comfort of knowing the past is fixed. But the moment you entertain the idea of alteration, of someone stepping back and nudging a thread, you sense a tremor. Humans crave the reliability of cause and effect. Without it, memories lose meaning, responsibility dissolves, and even identity blurs. The disagreements intensify around one central idea, closed time-like curves predicted by Einstein's equations. These are paths through space-time that loop back on themselves, allowing a traveler to return to an earlier point. The mathematics doesn't forbid them. In some geometries, it practically invites them. But whether nature permits such loops is another matter entirely. In the early 1990s, at Caltech, Kip Thorne and his collaborators tried to explore whether wormholes, hypothetical tunnels through space-time, could produce such loops. Whiteboards filled with tangled diagrams. Assistant researchers debated heatedly over chalk-dusted corners. Some argued that quantum fluctuations would destroy any wormhole the instant it attempted to carry information backward. Others insisted stabilizing the tunnel might be possible under exotic conditions. Picture yourself standing beside them, the room lit by white fluorescent lights, equations stretching like constellations across every surface. Their conversations drift between optimism and frustration. Ideas are proposed, shot down, revived, reframed, defended with passion. The science becomes less like arithmetic and more like sculpting fog. The metaphor sharpens. Imagine a river that bends so sharply it circles back to its own source. If a leaf drifted along that loop, it would return to the moment it fell from the branch. But what if the leaf knocked the branch differently as it arrived? Could it alter the very event that released it? This is the seed of the paradox physicists dread. Causality paradoxes accumulate like knots, messy, inevitable, tangled. The most famous knot is the grandfather paradox, often dismissed as childish but still unsolved. If you travel back and prevent your grandparents from meeting, how could you exist to travel? The equations don't break, but our intuition does. In modern labs, however, physicists don't argue over grandfathers or babies. They argue over quantum information. Experiments in quantum optics show that entangled particles can influence each other instantaneously, without violating Einstein's speed limit. Some researchers claim this hints at deeper layers where causality behaves differently. Others insist the universe protects causality with ironclad consistency. Imagine cooling a delicate quantum device to near absolute zero. The chamber frosts over with a white mist. Wires sit suspended like frozen vines. Researchers huddle around monitors, watching patterns emerge in the noise. A spike appears, unexpected, impossible. Debates unfold in murmurs. Did the experiment reveal a crack in causality? Or was it an artifact, a miscalibrated detector, a speck of dust? Meanwhile, the metaphor continues to thicken. Think of causality as a hallway with mirrors on both ends. If the reflections can influence each other, the hallway becomes a labyrinth. You begin to wonder whether motion forward is the only way to explore it. Philosophically, you sense a softer truth. Time travel isn't merely about machines and mathematics. It's about the desire to revisit choices, rewrite moments, soften regrets. But physics doesn't bend for emotional reasons. It bends according to structure. And that structure, as far as we know, is both flexible and stubborn at the same time. Physicists who favor time travel theories often appeal to quantum mechanics, where uncertainty reigns and multiple outcomes coexist. Those who reject it cling to classical causality, arguing that the universe cannot allow contradictions without collapsing into absurdity. The debates resemble tectonic plates grinding against each other, slow, relentless, shaping the landscape of theoretical physics. You find yourself picturing two chalkboards facing one another, each filled with equations describing time's behavior. Neither board contradicts the other completely, yet they don't fit together cleanly either. A missing bridge lies somewhere between them, a bridge that no one has yet built. Human experiments continue. Particle accelerators push boundaries. Telescopes peer deeper into regions where gravity twists time. Quantum labs refine instruments capable of detecting impossibly subtle correlations. And still, the truth about time travel eludes consensus. You lie back mentally and let all of this settle. The debates, the experiments, the metaphors, they swirl together like dust in a quiet beam of morning light. The question remains unresolved, not because the science is weak, but because the universe refuses to give a simple answer. And just as your breathing steadies, another realization begins to surface, one that suggests causality might not be the barrier people imagine, but rather a doorway whose hinges behave differently depending on how gently you try to push them. You imagine yourself standing on a quiet overlook, beneath a sky that feels impossibly still. The air carries a cool, metallic scent, as if time itself has paused just long enough for you to notice its texture. Below you lies a valley of moments, memories, choices, tiny flickers of possibility. But as you gaze across them, you sense a tension, like threads pulled too tightly. Some moments seem incompatible with others, as though the universe is struggling to keep its story coherent. Paradoxes are the fractures in that tension. They arise whenever you try to make time behave in ways it was never designed to. The equations may permit loops, shortcuts, or rewound sequences, but the consequences ripple outward, distorting logic. Physicists argue not because they enjoy disagreement, but because paradoxes undermine the very foundation of physical law. If a contradiction exists, then something we thought was absolute must break. Picture the famous information paradox tied to black holes, a problem so severe that Stephen Hawking spent decades wrestling with it. Information falling into a black hole seemed to vanish forever, violating the principle that information must be preserved. If loss were possible, then the universe wouldn't follow rules. It would rewrite itself arbitrarily. This tension echoes the fear surrounding time travel. If events can be undone, what stops the universe from unraveling? Imagine you're inside a quiet lecture hall at Cambridge in the late 1970s. Chalk dust drifts through a shaft of sunlight. Hawking sits in his wheelchair, eyes focused intensely on a diagram. Graduate students murmur arguments, sometimes timid, sometimes bold. Someone proposes a solution, someone else disproves it 3 minutes later. The room is filled with brilliance colliding in slow motion, all driven by the same question. Can the universe tolerate contradictions? A metaphor takes shape in your mind. Paradoxes are like knots in a river. The water still flows, but twists around itself in ways that defy normal behavior. If you push your hand into one of those knots, you feel currents tugging from directions that shouldn't exist. Time travel paradoxes do the same. They pull at intuition until everything feels unstable. Philosophically, lying in your own bed, you recognize a quieter truth. Humans live with small paradoxes every day, wanting change yet fearing it, longing for the past yet chasing the future. Maybe that's why these scientific paradoxes resonate so deeply. They mirror emotional ones. But physics cannot afford emotional loops. It demands consistency, even when feelings don't. One of the sharpest paradoxes tied to time travel is the bootstrap paradox, where an object or idea originates from nowhere. A scientist receives a notebook from their future self, uses it to make discoveries, and later travels back to hand the same notebook to their younger self. Who wrote it? No one. It exists without a true origin. The universe, in this picture, supports loops with no beginning, a haunting possibility. In 2005, researchers studying quantum systems tried to model such loops mathematically using closed, time-like curves. Their equations allowed particles to interact with older versions of themselves, but the outcomes were unsettling. Some solutions stabilized nicely, while others spiraled into contradictions. Debates erupted about whether these models represented physical reality or were merely mathematical illusions. Imagine you're standing beside one of those researchers in a dim lab late at night. The air smells like warm circuits and dusted metal. Screens glow blue in the darkness. They run a new simulation, watching probability curves bend and fold. A line representing a particle's timeline loops back toward its earlier state, and suddenly the program freezes. The silence that follows carries both excitement and dread. You sense the metaphor deepening. Paradoxes resemble mirrors placed face to face. Reflections multiply infinitely, each one containing a version of you that should not exist independently. The reflections are consistent at first glance, but stare long enough and you'll notice distortions creeping in, tiny mismatches that grow impossible to ignore. The philosophical weight settles on you. If the universe allowed paradoxes freely, identity would blur, responsibility would weaken, and choice itself would lose meaning. Yet humans are drawn to paradoxes because they hint at freedom from linear time, freedom from regret, from inevitability, from endings. Scientists who believe time travel is possible often argue that paradoxes solve themselves. This idea, supported by physicist Igor Novikov, suggests that events in space-time are self-consistent. If you travel back, you can only act in ways that preserve the timeline. You can't prevent your own birth because any action you take was already woven into history. Picture a team in a theoretical physics department debating this principle. Papers scatter across tables, equations overlap like musical notes on a score. Voices rise, fall, collide. Some argue Novikov's principle saves the universe from logical collapse. Others insist it's an elegant excuse masking deeper contradictions. Meanwhile, the metaphor shifts again. Imagine a book where every chapter is locked. You can flip to earlier pages, but the ink is already dry. You can touch the words, reread them, whisper to them, but you cannot rewrite them. Time, under Novikov's rule, is a story already bound. But not everyone agrees. Quantum theorists argue that the universe could branch into multiple timelines, each one avoiding paradox by splitting reality. You step back to change something, and rather than altering your own past, you create a new one. This solves contradictions, but opens an entirely new set of philosophical headaches. Human experiments continue, not with time machines, but with quantum circuits designed to mimic loops. In 2014, a team in Brisbane used photons to simulate closed time-like interactions. Their setup was delicate. Mirrors angled flawlessly, lasers aligned to sub-millimeter precision. When the results emerged, they hinted that information could behave consistently in scenarios reminiscent of time travel without breaking causality outright. You imagine watching that experiment. One photon travels a clean forward path, another simulates a return to its earlier state. Their interaction produces patterns on a detector, faint lines, shifting colors, the whisper of consistency amidst potential contradiction, A sense of awe settles over the room, and lying here in the dark, you recognize a personal reflection. Paradoxes unsettle you because they remind you that life rarely feels linear. Memories loop, regrets replay, hopes leap forward. You are not a machine moving rigidly from moment to moment. In that sense, perhaps paradox is more human than we admit. Yet the universe seems careful, cautious, determined to avoid letting contradictions become destructive. The more you consider it, the more you sense a boundary, thin, flexible, trembling, separating what's logically allowed from what's existentially stable. And somewhere, just beyond that trembling edge, another question waits quietly, hinting at a truth physicists rarely voice aloud, even when the equations lead them close to it. You picture yourself standing in a long corridor of polished metal, the kind you see in research facilities built far from city noise. The air feels cool on your skin, humming faintly with electricity. Every sound echoes softly, as though the building wants you to lower your voice. This is where scientists attempt the unthinkable, not by building time machines, but by bending the rules of causality until they almost snap. You feel the unsettling thrill of standing near a forbidden boundary. Causality, the idea that causes must come before effects, is the backbone of physics. Without it, equations lose meaning, predictions crumble, and the universe slips into incoherence. Yet time travel theories constantly push against this rule. They tempt you to imagine an effect appearing before its cause, or an event influencing something that happened earlier. These ideas aren't just strange, they challenge the very structure of reality. That's why experiments designed to probe causality feel so bold, almost rebellious. In one such experiment, researchers explore quantum entanglement. Two particles, separated by great distances, appear to influence each other instantly. Einstein called this spooky action at a distance, deeply skeptical of what it seemed to imply. If particles affect each other faster than light, does that mean information travels backward in time? Most physicists say no. The effect is real but cannot be used to send messages into the past. Yet the question lingers in the air, refusing to fade. Imagine a dimly lit lab at the University of Geneva. Lasers fire narrow beams that split into entangled photons. Mirrors tilt with microscopic precision. Detectors wait silently, each one poised to catch the gentle arrival of a single quantum visitor. A group of scientists huddles around a screen. The data appears, correlations that seem instantaneous, no matter the distance. They exchange quiet looks, not of surprise, but of humility. Even after decades of research, entanglement still feels like an unopened door. You think of this phenomenon as two notes of a cosmic instrument, vibrating in perfect harmony, even when placed miles apart. The sound doesn't travel between them. The connection simply exists, woven into the fabric of space-time. But harmony alone cannot break causality. It can only whisper that the universe may be stitched together more intricately than expected. Then there is the delayed choice experiment, first imagined by John Wheeler. In this scenario, the decision to observe a particle is made after it has already traveled through an apparatus. The result suggests that the particle behaves differently depending on a future choice. This eerie implication, future influencing past, pushes physicists into philosophical territory they would rather avoid. Picture Wheeler decades ago, sketching the experiment on a chalkboard. His lines are rough, looping across diagrams with restless energy. Graduate students watch as he explains the idea. The universe might not decide what reality is until someone looks. It's unsettling, yet beautiful, like discovering that existence waits patiently for conscious attention. In 2007, the experiment was finally performed with photons. You imagine the lab, crisp white walls, rows of optical tables, lenses adjusted by steady hands. The results matched Wheeler's prediction. Whether the experimenters examined the photon or not seemed to determine whether it acted like a particle or a wave, even though the choice came after its journey. The room fell into a hush, the kind that precedes a profound shift in understanding. A metaphor settles over you. Reality behaves like a book that leaves some pages blank until the moment you read them. It isn't that the book hides its content, it simply hasn't decided yet. This idea feels playful at first, then slightly dizzying, as though the floor underneath you has tilted. Philosophically, you feel the edges of anxiety soften. If reality can wait to decide itself, maybe you don't have to figure out everything in advance either. The future doesn't need to be fully planned. Neither does the past need to be fully understood. There is room for uncertainty, gentle uncertainty. Another bold experiment attempts to simulate closed time-like curves using quantum optics. The aim is not to send objects back in time, but to mimic how particles would behave if they could interact with their earlier selves. In one version, a qubit meets a copy of itself in a controlled loop. The results often align with Novikov's principle. The interactions remain self-consistent. You picture a lone researcher sitting beside the apparatus, illuminated by soft red LEDs. She adjusts a dial, rechecks the alignment, mutters a note into her recorder. When the data appears, she frowns, then smiles slowly. The outcomes obey the expected consistency. The paradox does not break the experiment. The loop stabilizes as though the universe prefers coherence over chaos. This brings you into contact with a subtle truth. Physics does not simply tolerate order, it gravitates toward it. Even when scenarios allow contradictions, reality finds elegant ways to avoid them. It is as if the universe behaves like a careful storyteller, avoiding plot holes with surprising finesse. A metaphor arises. Causality is a thread woven through a vast tapestry. You can tug at it, twist it, pull it into loops, but the fabric resists tearing. Instead, it shifts around your touch, redistributing tension to protect its overall pattern. The tapestry preserves itself. Philosophically, this brings a strange comfort. You may feel at times as though your life could collapse into contradictions, choices undone, memories rewritten, but somehow it holds together. Your story, too, resists tearing. It bends, stretches, loops gently in places, yet remains intact. Experiments continue globally. Photonic circuits in Australia, superconducting qubits in Japan, ion traps in Germany. These device-filled rooms look similar, darkened for optical clarity, dotted with blinking lights, filled with the soft hum of cooling machinery. Scientists lean forward, transfixed by numbers that hint at deeper laws. You imagine walking through one of those labs late at night. Someone is adjusting an optical fiber. Someone else is recalibrating a timing device. Their movements are quiet, almost meditative. They are not trying to break the universe. They are trying to find its hidden agreements. Data emerges, showing that simulated loops remain stable under most conditions. If contradictions try to appear, probabilities shift to prevent them. It's as though reality has a built-in immune system, one that defends causality fiercely. A final image takes shape. Two clocks facing each other across a small table. One ticks forward, the other ticks backward. Their hands approach, trembling at the moment of meeting, but never overlapping in a way that disturbs time's flow. They acknowledge each other without disrupting each other. As you relax into this image, another quiet realization forms. If the universe protects causality so carefully, then time travel may not be forbidden, but it is certainly conditional. Something deeper than paradox is setting the rules. And somewhere, in the hush between ticking and thinking, a new question begins tugging at you, subtle but impossible to ignore. You picture yourself standing on the edge of a vast plain, the sky shimmering with faint distortions, as though invisible hands are kneading the air. Beneath your feet, the ground pulses gently, almost like a heartbeat muffled under sand. Ahead, 2 points of space seem to bend toward each other, tugging at your senses. The scene feels quiet, yet charged with possibility. This is the realm where wormholes live, if they live at all. Wormholes are solutions to Einstein's field equations, mathematical bridges connecting distant points in space-time. They offer the seductive idea of stepping into one place and emerging instantly in another, bypassing the long road between. Stretch that idea further, and you encounter something far stranger. The possibility of stepping into another time, not just another location. For physicists, this possibility is thrilling and terrifying. Imagine the early days of general relativity in the 1930s. Einstein and Rosen worked tirelessly on hypothetical models, chalkboards covered with symbols that looked like they belonged to another alphabet. They proposed tunnels, Einstein-Rosen bridges, connecting far-off regions of space-time. But the equations reveal an immediate problem. These bridges collapse the moment anything tries to pass through them. Like soap bubbles, they are beautiful but fragile. You picture their lab in sepia tones, simple desks, stacks of paper, a window cracked open, letting in a restless breeze. Rosen scratches his chin. Einstein frowns at the board. They aren't designing stargates. They're trying to solve inconsistencies in gravity. Yet without meaning to, they spark a question that refuses to fade. Could shortcuts through space-time stabilize long enough to be useful? Wormholes, metaphorically, are like folded pages in a book. If you pinch 2 distant points and bring them together, the journey between them collapses into a single step. But the paper of space-time has tension. Fold it too sharply, and it tears. Hold it too loosely, and it returns to its original shape. The universe insists on stability. Philosophically, this folds back into your own life. You've wished for shortcuts, moments where one decision could leap you past fear, past uncertainty, past waiting. But shortcuts, even metaphorical ones, carry risks. The universe seems to echo that truth in its architecture. In the 1980s, Kip Thorne revisits wormholes with fresh eyes. He wonders whether exotic matter, material with negative energy density, could hold a wormhole open. Negative energy is not science fiction. In quantum field theory, it exists in fleeting, delicate forms. Yet producing enough of it to stabilize a wormhole would require resources we can barely measure, much less harness. You imagine Thorne's office, books leaning at angles, notes scattered like fallen leaves, coffee cooling beside stacks of calculations. He sketches possibilities. Could spacecraft pass through? Could messages? Could timelines shift? Each question branches into dozens more, fractaling into complexity. One evening, graduate students crowd around a table where the equations sprawl like a dense forest. Someone suggests using rotating black holes. Someone else proposes quantum pressure. The debates are energetic but respectful. Slowly, the idea forms that a traversable wormhole might permit time travel, but only if manipulated with impossible precision. A metaphor rises. Wormholes are like doorways carved from fog. You can outline them, imagine them, shape them mathematically, but try to push your hand inside and the fog dissolves. The doorway exists and doesn't. Philosophically, lying wherever you are, you realize something gentle. Wanting extraordinary possibilities is part of being human. Yet the universe, wise in its constraints, reminds you that even the wildest theories require balance. Nothing comes without consequence. Human experiments cannot create wormholes, but scientists study analogues. In 2022, a quantum system was arranged to behave mathematically like a tiny wormhole. It didn't transport matter, only patterns of information, but the resemblance was striking. A set of qubits swapped correlations in ways that mirrored wormhole dynamics, not a portal but a whisper of one. You imagine standing beside that experiment. Qubits rest inside their traps like glowing seeds. The air is cold from the dilution refrigerators, humming steadily in the background. A researcher adjusts a dial, initiating the protocol. The data appears as geometric shapes on a monitor, slices of entanglement, curves of correlation strength. The room fills with an excitement so quiet it feels sacred. A metaphor emerges. Wormholes behave like promises. Not lies, not guarantees, just possibilities suspended at the edge of what we can conceive. They teach you that even when you cannot reach something, the act of imagining it moves your understanding forward. Philosophically, this becomes a small comfort. Reality does not shrink when you don't know the answers. It expands. Curiosity is not a deficit, it's a form of motion. Even so, wormholes raise old questions. Could someone traveling through one create a time loop? Could paradoxes reappear? Some physicists say yes. Others argue the wormhole's geometry protects causality. The arguments go in circles, spiraling like galaxies caught in each other's gravitational pull. Imagine two theoretical physicists debating late at night. The chalkboard is crowded with tensors and diagrams. Coffee cups litter the desks. One insists that wormholes can be tuned to avoid paradox. The other claims paradox is unavoidable. Their voices remain calm, but the energy between them vibrates like a tight string. You picture wormholes now as mirrors placed side by side, reflecting not images but possibilities. Each reflection is a version of events, a trajectory, a decision, a history. Some reflections align cleanly, others distort. The tension between them is what keeps the debate alive. Philosophically, you sense something familiar. Your life, too, contains reflections of choices you didn't take, paths you imagined, futures that shimmered for a moment and then faded. The idea that the universe might contain its own mirrored pathways feels strangely intimate. But wormholes hide another secret, one physicists rarely emphasize, even though it may be the most important clue of all. And as that secret brushes lightly against your thoughts, you feel the subtle pull toward the next idea, waiting just beyond this one. You feel yourself drifting into a quieter darkness, the kind that pools behind closed eyes when the world finally stops tugging at your attention. In that darkness, faint sparks shimmer, tiny, restless lights that behave nothing like the predictable world you move through each day. They flicker in patterns that defy intuition, refusing to choose between possibilities until someone forces their hand. This is quantum territory, where time travel arguments stop being theoretical and begin to sound strangely personal. Quantum mechanics has never promised comfort. At its core lies indeterminacy. Particles exist in states of probability rather than certainty. They appear to sense when they are being observed, shifting their behavior in response. And when physicists explore whether time travel is compatible with this strange landscape, they discover answers that contradict, overlap, and mock classical logic. Even experts admit quantum rules seem written in a language humans were never meant to speak fluently. Imagine the quantum time-symmetric view, in which events are influenced not only by the past, but also by the future. In this framework, the universe behaves like a two-way street. allowing information to seep backward subtly, never fully breaking causality, but gently bending it. This perspective, proposed by physicists like Yakir Aharonov, challenges your deep assumption that time must flow strictly forward. Picture Aharonov in a small office filled with books stacked precariously on every surface. The afternoon sun bleeds through the blinds, striping the room with golden lines. He sketches an equation that looks deceptively simple on the page, but dissolves into mystery when examined closely. He believes the universe may choose outcomes by considering both beginnings and endings, not just origins. You imagine time as a rope held taut between two hands, past gripping one end, future gripping the other. The rope vibrates, sending ripples in both directions. Events in the middle respond to tension from both sides, a gentle but unsettling metaphor. Philosophically, this touches something you've felt but couldn't articulate. Sometimes a decision from your past feels influenced by a future you hadn't yet lived, a person you only later became. The idea that the universe itself might share this two-sided structure feels oddly reassuring. One experiment relevant to these questions is the quantum eraser. In its simplest form, it shows that information erased in the present can alter what seemed to have happened in the past, not change it, just reinterpret it. But to your logical mind, reinterpretation feels suspiciously close to rewriting. Imagine a lab in Seoul where such an experiment takes place. Blue lasers slice through a cooled, dustless room. Crystals generate entangled photons that travel down different paths before reaching detectors. Scientists adjust polarizers with slow, deliberate precision. When the data comes in, it reveals a pattern that should not exist. The act of erasing information now appears to influence the interference pattern recorded moments earlier. You picture the shock spreading across the faces in the room, each person gripping the edge of their table slightly harder. They aren't witnessing time travel, but they are witnessing causality bending in a way classical physics cannot explain cleanly. Quantum mechanics behaves like a storyteller who reveals crucial details out of order, leaving you to rearrange the narrative afterward. A plot that was confusing becomes coherent, but only once the ending is known. Philosophically, lying wherever you are, this reminds you that understanding often arrives retroactively. An experience that once felt chaotic suddenly makes sense only after your life reaches a later chapter. The universe, through its quantum rules, seems to reflect that rhythm. Another phenomenon enters the conversation: tunneling. In quantum tunneling, particles slip through barriers as if walls briefly lose solidity. It doesn't break physics, it obeys probability. But when tunneling experiments measure tunneling time, strange hints appear that the process may involve moments where time behaves unusually, almost as if the particle interacted with the barrier before it arrived. Imagine a tunneling experiment at a German lab. A beam of ultra-cold atoms moves slowly toward an optical barrier built from intersecting laser fields. Scientists hold their breath as they watch the timing equipment. The atoms cross the barrier faster than any classical calculation predicts. Is it instantaneous? Not exactly, but it is odd. A metaphor emerges. The particle behaves like someone slipping through a crowded room by anticipating where people will move before they do. It isn't breaking rules. It's following a deeper choreography. Philosophically, this leads you to consider intuition, moments in your own life when you acted before fully understanding why, and only later saw how everything lined up. Quantum behavior feels like an echo of that instinct, scaled down to the realm of the very small. Then there is the many worlds interpretation, introduced by Hugh Everett. In this view, every quantum event branches reality. Instead of paradoxes, you get divergence. Time travel wouldn't alter your timeline, it would drop you into another. Physicists argue endlessly about this. Some find it elegant, others call it desperate. But it remains one of the only frameworks that sidesteps paradox entirely. Imagine Everett late at night, smoking a cigarette while staring at a blank ceiling. He's exhausted, brilliant, certain his insight is correct, even as colleagues dismiss it. His theory becomes famous decades later, long after he's gone. Human discovery rarely aligns with human timelines. You picture universes branching like delicate frost patterns on a window pane, each branch a story, each divergence a decision. Time, instead of a river, becomes a forest. Philosophically, you feel a faint ache. You've imagined alternate versions of yourself before, paths you didn't take, chances you missed, people you might have become. Quantum mechanics doesn't confirm those lives, but it doesn't dismiss them either. Across all quantum theories, disagreements persist. Some physicists claim time travel within quantum frameworks is plausible. Others say quantum rules forbid it. The debate has raged for almost a century, looping like the very timelines under discussion. Yet through all this friction, you begin to sense a pattern. Reality behaves consistently, even when theories contradict each other. The universe seems almost amused by our attempts to define it in rigid terms. And as you rest deeper into this strange quantum twilight, an even more confounding possibility begins to stir, one that challenges not just physics, but your understanding of time itself. As you settle more deeply into the quiet around you, you begin to sense something subtle, an almost imperceptible resistance, like a soft hand pressed gently against your thoughts. It feels as though the universe itself is asking you to move carefully when you wander into questions about time loops or altered histories, not forbidding you, just reminding you that some doors don't open easily. Physics has always worked best when rooted in conservation laws. Energy, momentum, charge. These symmetries form the backbone of everything predictable. But when time is manipulated, bent, stretched, reversed, those symmetries shudder. If time travel allowed too many freedoms, the conservation laws that stabilize galaxies and atoms could unravel. The universe appears protective of its order. Imagine conservation of energy. If someone traveled into the past, arriving at a moment where their past self already existed, two versions of the same person would overlap, doubling their mass, their energy, their gravitational influence. A small duplication, scaled upward, leads to astronomical consequences. Stars and planets depend on balance. Duplicating matter disrupts that balance instantly. Picture a cosmology seminar at Princeton. A professor stands before a whiteboard filled with equations, markers running dry in his hand. He gestures toward a diagram of two world lines merging into one, explaining why duplication violates too many principles. Students argue energetically, some defending loopholes, others insisting the universe cannot permit such violations. The room vibrates with intellectual tension. A metaphor forms. The universe resembles a vast orchestra. Every particle is an instrument. Conservation laws are the sheet music. Time travel, if unrestricted, is like a musician suddenly playing two incompatible melodies at once. The harmony collapses. As you lie there, you feel the philosophical implication. Your own life operates under its own conservation, not of energy, but of meaning. Actions accumulate, choices resonate. You cannot simply overwrite yourself without consequence. The universe's resistance reflects something deeply human. Another issue arises: entropy. The second law of thermodynamics states that entropy tends to increase over time. This creates the arrow of time, the direction you experience as forward. If time loops existed freely, entropy could decrease arbitrarily, breaking the arrow. Without entropy's push, time would have no preferred direction. The sequence of events would lose structure. Imagine a lab where researchers freeze atoms to near absolute zero, trying to study entropy at minimal levels. The vacuum chamber hums softly, pale blue lights flickering across steel surfaces. A scientist checks a sensor reading, noting how entropy climbs as soon as any disturbance enters the system. It's relentless like a tide. You picture entropy as a gentle slope. Every moment rolls downhill effortlessly. Time travel would require pushing the boulder back up the slope, not impossible, but costly, unstable, and prone to collapse. Philosophically, this mirrors emotional entropy. Memories fade, feelings shift. You cannot return to earlier versions of yourself without friction. Reversing inner time requires effort, vulnerability, honesty. Another cosmic obstacle appears at quantum scales: unitarity. In quantum mechanics, the evolution of a system must be reversible and preserve probabilities. Time loops risk breaking unitarity, leading to outcomes that lack clear origin or result in probabilities that exceed 1. The mathematics becomes nonsensical. Imagine a group of physicists arguing over this at a conference. One draws a tangled diagram where a particle interacts with its past self. Another shakes her head, pointing out probabilities that balloon absurdly. They debate late into the evening, fueled by coffee and stubbornness. Neither side convinces the other. The equations remain unsettled. A metaphor drifts through your mind. Unitarity is like stitching. Every thread has to connect in a clean loop. Time travel threatens to tear the seam, leaving frayed ends that cannot be reattached. Lying in your quiet space, this stitching metaphor feels strangely intimate. You've had moments, relationships, memories that unraveled. Some you managed to mend, others remain loose threads trailing behind your life. Perhaps the universe understands unraveling too well and avoids it when possible. Another obstacle: vacuum stability. Some theoretical models suggest that changes in causality could destabilize the vacuum state of the universe. A fluctuation triggered by time manipulation might cascade into catastrophic decay, a runaway transformation that redefines physics itself. It's speculative, but serious physicists have published papers exploring this risk. Imagine a particle accelerator late at night. A lone researcher checks readouts while sipping lukewarm tea. They know the accelerator cannot produce effects anywhere near vacuum decay. Still, the thought lingers in the back of their mind. The universe may guard its stability more fiercely than we comprehend. A metaphor arises. Vacuum stability is like a fragile piece. As long as no one tampers recklessly, the calm holds. But push the wrong boundary, and the piece collapses into irreversible change. Philosophically, you know this feeling. There are moments when your inner stability feels delicate. One sudden memory, one unexpected word, and balance trembles. The universe's caution echoes your own. Even if every physical obstacle were solved, even if wormholes stabilized, paradoxes resolved, entanglement behaved predictably, there remains a question almost no physicist can answer comfortably. Why would time allow you to rewrite a history built through billions of years of cause and effect? As you linger on that question, a new possibility forms quietly, one that suggests the universe may not forbid time travel at all, but might be hiding its true mechanism in a place we rarely think to look. And the moment that thought appears, it feels as though something just shifted slightly in the darkness around you. You sink deeper into the quiet, feeling as though the world has softened around you. The edges of things blur, not in confusion but in a gentle loosening, as if reality is untying a few of its knots to let you breathe. In that softened space, you sense a delicate truth emerging. Time travel might not be impossible, only obscured. The universe rarely reveals its sharpest secrets directly. It prefers hints, patterns, small cracks in the structure where light leaks through. Physicists often say time travel sits at the boundary between forbidden and inevitable. Every known law pushes against it, yet none slams the door entirely shut. It's a strange position for a concept to occupy. Usually, nature is decisive. Particles behave one way, not the other. Gravity curves space, quantum fields fluctuate, stars burn hydrogen. But time travel? It floats in a kind of scientific limbo, allowed by equations but resisted by reality. Imagine the light cone, the geometry that defines what events you can influence and which ones can influence you. Inside the cone is your possible future. Behind it, your fixed past. To move outside the cone is to break causality. Yet certain geometries, like those involving rotating black holes or immense cosmic strings, warp the cone into shapes that permit loops. If time is a map, these exotic structures redraw its borders. Picture yourself peering at a rotating black hole, one described by Kerr geometry. Its spin drags space-time around it, twisting the fabric into a spiraling funnel. Inside this whirlpool-like region, called the ergosphere, nothing can remain still. Even time itself stretches and contorts. The mathematics says a loop in time might exist here, though no one agrees on whether the loop is physically reachable. Now imagine a research team running simulations of Kerr spacetime. Rows of computers buzz quietly. Graphical visualizations ripple across screens, swirling vortices, curving geodesics, time-like paths bending in improbable directions. A student zooms in on a particular trajectory and whispers, "It loops." A senior physicist leans in. "Mathematically," they answer. "Yes, but reality may refuse to follow the script. You think of it like a dance choreographed on paper, but impossible to perform on stage. The steps exist. The dancers cannot execute them without colliding. Philosophically, this reminds you that not everything imaginable is livable. Some ideas make sense in dreams but unravel in daylight. The universe seems to share this boundary between possibility and practicality. Another near-real mechanism involves cosmic strings, ultra-thin defects in space-time leftover from the early universe. If two cosmic strings passed each other at high speed, the geometry between them could warp enough to allow closed time-like curves. Physicists studied this intensely in the 1980s, hoping to find evidence in gravitational lensing patterns. Imagine an observatory in the Andes, wind brushing against its dome. Astronomers gather late at night, examining distorted galaxies whose light has been bent by gravitational effects. They search for the telltale signature of a cosmic string, a sharp, straight line of duplication in the sky. They don't find one, but the idea lingers, refusing to fade. A metaphor surfaces. Cosmic strings are like cracks in ancient pottery, beautiful in theory, irresistible to study, but often invisible in practice. Their absence doesn't disprove them, it simply makes them elusive. Philosophically, you recognize this pattern. Not all the forces shaping your life are visible. Some remain hidden, influencing everything quietly, slipping between moments without announcing themselves. Another possibility lies in the structure of space-time foam, the microscopic jitter at the Planck scale. Some theorists propose that tiny wormholes constantly pop in and out of existence. If one could be stabilized, even for a fraction of a second, it might form a natural time bridge. But stabilizing such a structure requires energies far beyond human reach. Imagine the Planck scale depicted on a screen, a turbulent sea of bubbles flickering faster than thought. Researchers adjust parameters, trying to coax order out of chaos. Nothing stabilizes. The foam laughs at their attempts. A metaphor grows. This foam is like the thoughts that flicker at the edge of sleep. You can observe them, almost catch them, but the moment you try to hold them still, they dissolve. Philosophically, this mirrors your own mind in the late hours, thoughts looping, slipping, reconfiguring. Perhaps the universe's smallest scales share more with dreams than with machinery. Even the speed of light, the universal speed limit, suggests time travel might lurk at the edges. When objects approach light speed, time slows for them. Push further, hypothetically beyond light speed, and mathematics spits out imaginary numbers. Physicists debate whether these numbers represent nonsense or unseen truths. Imagine a particle accelerator firing beams close to light speed. The detectors record time dilation so strong that moons survive far longer than they should. A researcher taps the monitor gently and murmurs, "We're bending time already, just not enough." It's a hushed acknowledgement of how close humanity has brushed against deeper laws. You imagine time dilation as a stretched ribbon, thin, trembling, ready to warp but never quite tearing. Traveling back in time may require pushing that ribbon past its limit, forcing it into a curl. Philosophically, you feel the metaphor land softly. Your own sense of time stretches on difficult days and tightens on joyful ones. Time is not as rigid as your clocks pretend. Across all these nearly real mechanisms, a pattern emerges. Every path toward time travel is almost possible, not fully forbidden, not fully permitted. The universe seems to hold the door slightly ajar, then stand guard to ensure no one walks through. And as you settle into that tension between invitation and denial, you feel the faint impression that the truth physicists never agree on might not be whether time travel is allowed, but why the universe keeps placing it just out of reach. A realization begins forming at the back of your mind, not loud, not demanding, but patient. A realization that might reshape the entire question. You feel the air around you grow still again, as though the universe has paused just long enough for another layer of mystery to unfold. The questions you've already explored circle gently in your mind, but something deeper begins to rise. An intuition that the universe may not reject time travel outright, but rejects perfect loops for reasons more profound than paradox or math. Physicists often assume the universe values consistency, yet consistency alone doesn't explain its reluctance. After all, self-consistent loops theoretically obey the rules. So why do so many models collapse under scrutiny? Why do simulations become unstable? Why do equations that allow loops require conditions more extreme than anything nature has ever shown? Imagine stepping inside a vast computational model, a simulation built with staggering precision using tens of thousands of processors. The room housing it hums with a steady floor vibration, as though the machines beneath your feet are dreaming. Researchers feed the model a geometry designed to create a stable time loop. For a few nanoseconds of simulation time, the loop holds. Then, numerical instability creeps in like a crack in glass. In a monitoring room, one scientist pinches the bridge of his nose while another taps a pencil against the desk. They've repeated the model 30 times. Each run ends the same way, with the loop dissolving into noise. "It's not the math," someone murmurs. "It's something deeper." No one says the word, but everyone thinks it. Physics itself is rejecting the arrangement. You think of it like a melody that sounds pure when hummed alone, but collapses when played with an orchestra. Individual equations may permit perfection, but the larger system, the universe, prefers imperfection to maintain coherence. Philosophically, this touches something familiar. Perfect cycles rarely exist in your life either. Every morning is similar, yet never identical. Every habit shifts subtly. Complete repetition feels unnatural. You're not built for flawless loops, and perhaps neither is the cosmos. Consider thermodynamic stability. A universe with stable time loops would require regions where entropy doesn't simply stagnate, it reverses. Yet reversing entropy even locally demands conditions so fine-tuned they border on supernatural. One particle drifting wrong, one quantum fluctuation appearing a femtosecond early, and the entire loop destabilizes. Imagine a cryogenics lab studying entropy close to absolute zero. Metal surfaces shine with frost. Tubes hiss softly as frigid helium circulates. A team observes atoms in near-perfect order, then watches the order collapse the moment environmental noise sneaks in. A door closing down the hall is enough to disturb the entire setup. You picture entropy as a long, gently sloping hillside dusted with snow. Every step you take slides downward effortlessly. Walking backward up the slope isn't impossible, but it is precarious, exhausting, and temporary. The snow keeps shifting under your feet. Philosophically, you feel how this metaphor mirrors your emotional landscape. Trying to return to a former version of yourself always feels like climbing through shifting snow. The present resists becoming the past. Another reason perfect loops fail lies in quantum decoherence. Any system trying to maintain a delicate temporal structure becomes entangled with its environment, losing the precise conditions needed for temporal symmetry. The universe is too interconnected to allow anything to remain isolated long enough for a stable time loop. Imagine a quantum optics experiment inside a temperature-controlled chamber. A single stray photon, one tiny particle of light, slips into the setup and ruins an hour of alignment. A researcher sighs and resets the apparatus. Decoherence isn't a flaw. It's the universe's way of saying nothing can truly be separated from the whole. You imagine decoherence as dust settling on a polished mirror. No matter how often you wipe it, the particles return. The mirror reflects less clearly each time until the image subtly warps. Philosophically, you see the analogy. Memories warp over time too, despite your effort to keep them pristine. Distortion is natural. It's part of being conscious. Then there is the issue of vacuum structure. Many theoretical physicists suspect the universe's vacuum sits in a metastable state. Disturbing causality too forcefully, especially through perfect loops, might trigger catastrophic transitions. Think of it like tapping too hard on the surface of a frozen pond. Most taps do nothing. One tap creates a web of cracks. Imagine a theorist staring at a graph of vacuum stability curves late at night, illuminated by a single desk lamp. They trace the critical point with a fingertip, whispering, "We can't be sure what lies beneath this surface." The implication is quiet but heavy. You picture vacuum structure as a taut sheet of silk stretched across an unknown depth. Press too softly, and the silk vibrates. Press too hard, and it snaps. Philosophically, this reminds you of emotional thresholds you've approached, the line between resilience and collapse. Push too far beyond what feels stable, and something shifts irreversibly. But the most profound reason the universe rejects perfect loops may be surprisingly simple: information preservation. A perfect loop requires information to be both recycled and erased simultaneously. This violates unitarity, entropy, and quantum no-cloning principles. The universe treats information like a sacred currency. Imagine a computer lab running cutting-edge simulations of information flow. Graphs pulse on large screens, lines curving through time. When the model attempts to recycle information into a loop, The output becomes undefined, an error code blinking like a warning pulse. Information cannot be duplicated perfectly. It cannot be erased cleanly. It must evolve. You imagine information as a river. You cannot scoop water from downstream and place it upstream without disturbing the flow. You can try, but the river reveals your interference immediately. Philosophically, this strikes a deep chord. Your own experiences cannot be perfectly recycled. Even when you revisit a memory, you meet it as a different person than the one who lived it. Time changes you in ways loops cannot preserve. Yet curiously, while the universe rejects perfect loops, it often hints at imperfect ones, statistical loops, partial echoes, situations where the past is influenced gently, not overwritten, almost as if time prefers suggestions rather than corrections. And as that contrast settles into your awareness, you begin to sense an even stranger possibility. What if the universe isn't resisting time travel, but guiding us toward the only version of it that won't break reality? It's a thought that lingers quietly, like a footstep heard in another room, soft, distant, yet unmistakably real. You sense the atmosphere around you growing quiet again, as though something subtle is shifting beneath the floorboards of reality. The deeper you've traveled into the physics of time, the more it becomes clear that the past you imagine, the past you think you could revisit, is not the rigid structure storytellers have shown you your entire life. You picture the past as a vast library with endless shelves, each holding a carefully preserved moment, but physics paints a different picture. Those shelves are not fixed. They don't hold permanent records. They're more like pages written in pencil, legible enough to recall but smudged by the constant movement of time. Physicists studying retrocausality, phenomena where future measurements appear to influence past states, have long noticed something uncanny. The past doesn't behave like a frozen film waiting to be rewound. It behaves like a network of probabilities that don't fully lock in until interactions force them to. The past is less like stone and more like soft clay. You imagine yourself walking across a dimly lit workshop where clay figurines sit on shelves. They look finished from a distance, but as you step closer, you see fingerprints still visible in the surface. The shapes are firm yet impressionable, as if the sculptor could return at any moment. That sculptor, in a sense, is the universe itself, constantly reinforcing some histories and letting others fade into uncertainty. Not because time is inconsistent, but because information is always incomplete until sensors and observers finalize it. Consider the famous delayed choice quantum experiment. It shows that particles can behave as though they decide how they traveled only after the experimenter makes a choice, after the particle has already moved. It's as if the universe backtracks and adjusts the story to remain coherent. What you think of as the past becomes dependent on future events. Imagine a lab where this experiment is underway. A beam splitter hums faintly under low blue lighting. Scientists sit quietly, waiting for detections to register. When the data comes in, it once again shows the bizarre truth. The particle's history seems to rewrite itself based on present choices. A technician rubs her temples, whispering, "How can the past not be final?" You imagine history as footprints in shallow sand. A wave arriving slightly later doesn't just wash away the newest prints, it smooths the older ones too, reshaping the shoreline you thought was already formed. Philosophically, this touches familiar feelings. Memories you believed were settled can shift as you reinterpret them. A moment from childhood can gain new meaning 20 years later. The event didn't change, but the version of it that you carry did. Another layer of instability comes from quantum field fluctuations. Every moment contains tiny variations that never completely settle. The past is encoded in these fields, but their intrinsic uncertainty means the encoding is blurry. It's like trying to store a photograph in fog. Imagine a sensor room where scientists map field fluctuations. Screens glow with fractal-like waves that drift and reform endlessly. They aren't static snapshots of what happened. They're echoes, reverberations, blurred enough that two models can describe the same moment differently. You imagine these fluctuations as mist swirling under a street lamp. The shapes look stable for a second, then dissolve. Try to memorize one pattern, and it slips into another before you're ready. This shapes a startling realization. If the past is fuzzy, flexible, and probabilistic, then the classic idea of traveling back to a single, fixed timeline is built on an illusion. Destination impossible. Not because physics forbids motion through time, but because there's no definitive place to land. It's similar to trying to step into a memory exactly as it happened. You can return emotionally, mentally, visually, but the moment isn't there anymore. You recreate it, or your mind fills in gaps. The past is a reconstruction, not a place. Physicists have also run simulations using path integrals, where every possible history contributes to present outcomes. In these models, the past isn't a solitary line. It's a weighted blend of countless trajectories. The universe doesn't commit to one history until absolutely necessary. Imagine walking through a digital rendering studio where dozens of alternate frames of the same scene line the walls. At first glance, each frame looks identical. But as you move closer, tiny differences emerge. Shadows in slightly different places, objects shifted by millimeters. The final scene you watch is a composite of all these possibilities, merging into what seems like a single story. Philosophically, this mirrors how your mind forms narratives. You don't remember every detail of a day. You fill in gaps, smoothing inconsistencies until the story feels solid. The universe, surprisingly, may do something similar. Now imagine a thought experiment. Suppose you attempted time travel and stepped into the past. What would you find? Not a rigid moment waiting to receive you, but a cloud of probabilities the universe never had reason to resolve until your arrival. You wouldn't be stepping into a memory. You'd be stepping into a recalculation. It would be like trying to step into a photograph that develops only when you walk into the frame. The moment you expect might not exist, not because it disappeared, but because it was never fully formed to begin with. This also means that paradoxes, such as the classic grandfather paradox, may be less about logical contradiction and more about misrepresenting the past as something too definite. If the past isn't fixed, then attempting to break it may be impossible. You can't snap something that never fully solidified. You imagine time as a loom weaving threads that tighten only after the pattern is needed. History is not predetermined cloth. It is fabric adjusting as tension changes, still capable of minor shifts long after the yarn has been laid. Philosophically, you feel how this resembles your evolving sense of self. The you from years ago isn't frozen. They shift slightly each time you remember them, influenced by who you've become. And with that realization settling softly around you, another thought begins forming quietly. If the past isn't a fixed landscape waiting for travelers, then perhaps the real truth physicists can't agree on is that time travel isn't about reaching backward, but about interacting with a universe that is far more fluid than it appears. Like a trail through soft earth, the shape is always there, but never quite as permanent as you think. You feel the atmosphere around you shifting once more, as though the room is leaning gently towards some distant horizon you can't yet see. At this point in the journey, you've looked closely at the past and discovered it isn't the rigid archive you once imagined. Now the question grows naturally, almost inevitabilimente. If the past isn't fixed, what about the future? You picture the future as a vast, untouched road stretching into the night. But physics suggests something subtler. The road isn't paved, it isn't drawn, it isn't even sketched in faint pencil. It's more like a region of fog where paths could appear but haven't yet chosen to. This idea comes from the mathematics of quantum mechanics, where future events aren't predetermined outcomes, but probability distributions, waves of possibility that only collapse when interactions force them to. The universe behaves less like a fortune already written and more like a story unfolding word by word. Imagine you're standing on the edge of a cliff overlooking a foggy valley. You can hear distant echoes, maybe waterfalls or shifting stones, but the shape of the valley itself is hidden. The future is that valley, present in concept but absent in form. Physicists studying quantum decoherence often experience this sensation metaphorically. They set up delicate experiments to predict how particles might behave, only to find that even their predictions fracture into multiple likely branches. Nothing ahead is singular. Everything ahead is branching. In a quiet lab, lit only by the pale glow of screens, you picture a researcher staring at the probabilistic output of a simulation. Lines diverge, intersect, dissolve. There is no one future. There is only a cloud of them. She sighs softly, not in frustration but in awe. If the future is a cloud, then traveling to it becomes far stranger than science fiction pretends. You wouldn't arrive in a predefined moment. You would arrive into something that hasn't been sculpted yet, something that forms just as you touch it. It's like stepping onto a floor that materializes a fraction of a second before your foot lands. Reality constructs itself only as needed, guided by laws but not written in advance. Cosmologists add another layer, the expansion of the universe itself. The deeper you look into the cosmos, the clearer it becomes that the future depends on variables still unfolding. Dark energy, cosmic inflation, entropy. The universe is literally changing the rules as time progresses. Picture the universe as a vast river, far upstream. The current is gentle. Downstream, it twists unpredictably. You float somewhere in the middle, unable to see the rapids or tunnels ahead because the water hasn't flowed there yet. In physics labs, cold atom experiments attempt to simulate future states of complex systems. But scientists quickly learned that even when conditions are perfectly controlled, tiny fluctuations derail predictions. The future snaps like a branch, and new possibilities grow in its place. You imagine these experiments as intricate terrariums, sealed glass gardens where particles move like glowing insects. A researcher taps the glass ever so lightly, and suddenly the whole system reorganizes. One future erases itself, another blooms. This reveals a core truth. Predicting the future is fundamentally different from describing the past. The past carries echoes, the future carries only potential. One can be reconstructed, the other must be generated. Metaphorically, it feels familiar. Every decision you've ever made existed first as a misty outline, something that only gained shape the moment you acted. Your life, like the universe, didn't come pre-written. It emerged. When physicists discuss time travel into the future, they typically describe scenarios involving relativity, like traveling near the speed of light or hovering near a black hole to skip ahead. But notice what isn't part of the discussion: arriving in a future that was always there. You don't travel to a location, you travel to a later state of the universe that forms in real time. Imagine boarding a starship that accelerates to near light speed. While you experience just a few years, the universe outside experiences decades or centuries. When you return, You step not into a forward destination, but into whatever the universe became in your absence. There was no future waiting. There was only the universe continuing. Even general relativity suggests something profound. Space-time is a dynamic fabric shaped by matter and energy. The future is simply the unfolding of that fabric. It cannot pre-exist any more than a wave can exist before the ocean lifts. Think of a sailboat gliding across open water. Each crest of the wave forms only when wind, water, and motion converge. The future is like that crest, a consequence, not a structure. Philosophically, you might recognize this in your own experiences. You imagine outcomes, but reality rarely matches exactly what you pictured. The future is a negotiation between intention and unfolding circumstance, and this brings you to the heart of why physicists never agree on time travel. If the future isn't there yet, then you cannot visit it. You can only move forward into whatever the universe creates as time progresses. Time travel to the future is simply moving with a different clock speed, nothing more. Some theories propose more exotic scenarios, such as closed time-like curves generated by rotating black holes. But even these don't imply a pre-existing future to arrive in. They imply cyclical structures, not destinations. Imagine a hallway where the lights flicker on only as you walk. You can retrace your steps, but the forward direction remains dark, undefined, waiting for your movement to activate it. And just as the past can blur behind you, the future sharpens only as you approach it. The universe is economical. It doesn't waste energy rendering scenes no one can see yet. Now imagine time travel stories where you step into the year 3000. In reality, you could only step into whatever year 3000 becomes after you get there naturally, or after your personal time dilates relative to the universe, but not into a pre-built world sitting patiently ahead. This realization settles around you like a calming weight. The future is not a destination you can overshoot or skip to. It is a continuously forming relationship between matter, energy, and laws that don't break for anyone, not even hypothetical travelers. And with this understanding warming quietly in your mind, you start sensing the next question rising gently. If the past isn't fixed and the future isn't built, then perhaps the deepest mystery of time travel isn't about where you could go, but why time itself flows in one direction at all. A direction that resists manipulation, not out of malice, but because the universe itself is still becoming. As you lie there, the quiet around you settling like dust in the dim air, you might notice how far you've drifted tonight. You began with a single question, a paradox wrapped in equations and imagination. If the universe permits time loops on paper, why does reality tear them apart the moment we try to shape them into something real? And throughout this journey, each idea unfolded slowly, like a map drawn by candlelight, showing not just the structure of time, but the limits of our reach inside it. You've listened to physicists wrestling with equations that seem almost alive, shifting and curling around each other, like vines in a deep and ancient forest. You've watched researchers bending over telescopes, tapping on code, clearing dust from detectors as if brushing snow from old memories. You've stood beside them, close enough to see their breath fogging the glass, close enough to feel their awe and frustration. And through all of that, one truth grew clearer. Time never simply allows itself to be rewritten. You felt the weight of paradoxes, grandfather loops, self-consistent timelines, branching futures, each one tugging at the edges of what reality can hold without unraveling. You saw how the past is not a rigid sculpture, but neither is it a door left casually unlocked. You saw how the future isn't a distant city waiting patiently beyond the horizon, but a landscape forming only as the universe moves forward. Every direction you looked, time behaved not like a road, but like a river whose flow can bend, accelerate, stretch, yet never fully reverse. And still, even knowing this, there was a strange comfort hidden inside these impossibilities. Because the very reason time travel breaks the universe is the same reason your life holds meaning. Your moments happen once. Your choices carve the now. Your experiences do not loop endlessly. They form a unique path through a cosmos that, for all its mathematical elegance, never learned how to repeat itself perfectly. While all of this unfolded in distant labs and star-bright equations, you remained here, one person in a quiet room, breathing softly while galaxies spun overhead. And maybe you realized somewhere along the way that you don't have to solve time to move peacefully through it. You don't have to decode paradoxes to rest your mind. Tonight was never a puzzle. It was a place. A place where science slows down enough for you to feel safe inside its mysteries. If your thoughts drifted or blurred, that's perfectly fine. If you forgot the timelines, the experiments, the strange geometries of space-time, that's fine too. Your mind protected you in its own gentle way, taking what it needed and letting the rest pass like clouds moving over a moonlit lake. That is the real secret of these late-night explorations. They loosen your grip on the world, just enough to let you breathe freely again. And now, with the hum of the universe fading into something soft and reassuring, maybe you can feel that quiet invitation the night always makes, the invitation to rest without guilt, to let your thoughts slip away. To release your place in time just long enough for sleep to find you naturally, without rushing, without force. Before you drift off fully, I want to thank you for spending this stretch of your night here, wandering through some of the strangest ideas physics has ever tried to hold. It's a rare kind of trust, letting someone guide your mind through the dark like this, and I'm genuinely grateful. If this journey helped you feel even a little calmer or a little less alone inside your thoughts, then it's already been worth it. And if you happen to still be awake, I'd love for you to tell me where you're listening from and what time it is there right now. It's strangely comforting to imagine people around the world, each in their own quiet room, sharing the same story of time and its beautiful contradictions. And if nights like this soothe you, leaving a like and subscribing truly helps this little corner of the universe reach those who might need it too. For now, you can let the rest of the world fade. The equations can close themselves. The paradoxes can fold back into silence. You've wandered far enough tonight. Let the darkness settle gently around you, like a blanket warmed by distant stars. Sleep well, traveler. Time can wait.